Hello students, welcome back. So we are discussing a very important chapter known as solutions. So in the previous lecture we have done some very important factual and theoretical portion of the chapter that dealt with types of solution. So I hope you have understood the type of solutions and you have done the problem solving as well. Okay, and I hope at the back you are also reading your NCERT book, which is a prescribed book for your JEE mains as well as advanced. So in the previous lecture we have discussed one very important concept of azeotrope. So I'm in a very quick glance, we are just going to revisit it. I'm just going to revisit the azeotropic portion. So basically we said that whenever we are considering a non-ideal solution, okay, non-ideal solution can be of two type. One was basically a solution that is showing positive deviation from the Raoult's law, and the other which is showing negative deviation from the Raoult's law. So in the positive deviation from the Raoult's law there was a pressure maxima. Okay, I hope you remember the graph, so I will just sketch it. I will show you a rough sketch of it. So when we plotted graph of positive deviation, so we said that the positive deviation graph would look something like this. If suppose we said that there are two components A and B, okay, the mole fraction of A is 1 over here, only pure component A is present. So when the mole fraction of A is 1, mole fraction of B would be 0. Mole fraction of B is 1 over here, so this is only pure B. Okay, so we were plotting the total vapor pressure, okay, versus the composition. So we said that this was the Raoult's line for the individual component. Okay, for the total one we were saying that just this was the total one. Okay, now any solution which is showing a positive deviation from Raoult's law will have this as the graph. Okay, so it shows a pressure maxima. So when we convert it into a temperature convert it into a temperature versus composition graph, so we were having a minima, right? I have already explained you this entire concept in the previous module. So hope you have gone through this. So we know that the component which is having higher vapor pressure is more volatile, so its boiling point would be less. So the pure boiling point of A is T0 A and the boiling point of B, pure B, is T0 B. Okay, so if we consider the temperature versus composition graph for a positive deviation solution, so we knew that there would be a minima over here. Okay, so the graph was something like this. Okay, so at higher temperature we were having vapor, at lower temperature we were having liquid, and in the region between the two graphs we were having both the phases, that is liquid in equilibrium with vapor. So we already discussed that this point is known as azeotropic point. So azeotrope is basically a constant boiling point. Azeotrope is basically a constant boiling point mixture that boils without change in the composition. What does that mean? It means that if we are boiling this solution whose suppose composition is this, so we are basically forming a azeotrope at this point. So when we boil the azeotropic solution, so it goes into the vapor phase without change in its composition. So whatever composition was there in the liquid, the same composition would be present in the vapor. Now when we condense back, we get back the original liquid. Okay, so we are saying that this azeotrope is behaving as a single liquid, as if there was not a two component system but it was a one component system. Okay, so we also did the fractional distillation concept. Okay, we said that suppose we are at this point. Okay, we took a solution whose composition is corresponding to this point. Okay, so when we heated it, we'll get the first trace of vapor. We condense that vapor. Okay, the composition of the vapor would be like on the vaporous graph. So if you drop a perpendicular, you will get the composition. So when you condense this vapor, you will get a liquid. So I reached a point B. Okay, now when again I started boiling it, so from B I went to this point, the trace of vapor would start appearing. The composition of this vapor would be corresponding to the vapor graph. Okay, so again I condense this back, so I get a liquid. So again what I do is I increase the temperature. So as soon as I reach this point, again the vapor would be formed. So this would be the composition of the vapor. I condense it back. Okay, now when I am heating it, okay, I am always stuck at this point. This is called as an azeotrope, because at this point when we heat this liquid at this particular composition, it has formed a azeotrope. So when we heat it, so both the component goes in the vapor phase, okay, without unchanging their composition. So whatever composition was there in the liquid, the same composition would exist in the vapor. Now when we condense back, we get the original liquid. So when we do it again and again, we are stuck at this point because the composition is not changing. So we will be stuck at this point, so we will not be able to carry out the fractional distillation for a azeotropic solution. Okay, same was for the negative deviation. Okay, negative deviation solution, we knew that there would be a minima in the pressure graph, so the graph would look something like this. Okay, so let me draw it with a blue pen so that you are able to understand it. So this would be the for the negative deviation. Okay, so the total pressure is always less than the pressure predicted by the Raoult's law. Because there is a pressure minima, so there would be a temperature maxima. So the graph would be something like this. Okay, so we'll get an azeotropic point over here. Okay, now again when we start doing the fractional distillation, we'll be stuck at this point, because when we reach this composition, okay, corresponding to the azeotropic solution, now whenever we try to distill the solution, we'll get the same composition mixture time and over again. So when we do the regular condensation and vaporization, so we'll get the same composition of the mixture every time, so we are not able to purify them. So we said that azeotropes are basically a constant boiling point mixture, okay, that distills without any change in its composition. So this is actually a very important concept, and I hope the graphical aspect of this is clear, and you have also memorized the examples of positive deviation, negative deviation, as well as the property of the positive and negative deviation solutions. Okay, so this was the main concept that we discussed in the previous lecture, and this is actually very important. Okay, if you will see the JEE papers, lot many theoretical questions are coming on these portions. Okay, so this is conceptual, this is having a lot of detailed analysis. So I hope you have understood this and you have made a good notes of it. Okay, so what I would recommend you to read now, if you are following this platform now regularly, you must have understood that we are going to the highest level, starting from the very scratch and going to the highest level. Okay, so now you need to take care that you are complementing this with a good reading, and you are doing the daily practice problem sheet solving as well, and you are reading a bit of portion. If you have read the NCERT, if you want to read some higher level content, you can definitely have a look at Peter Atkins. So there is a physical chemistry book by Peter Atkins. It is basically followed in the universities, but it has a very good idea about these things. So when you read it, your mind will become more skillful, you will absorb new things, you will exactly come to understand how scientifically things are driven. Okay, so as I have already told you, the preparation is not for any entrance examination, the preparation is for understanding of the subject and making us better each and every day. In the process, if the process is right and you are following whatever has been said to you, your level will definitely rise, and after some point of time you will see that you have started to perform in a much better and a much efficient manner. So I hope you are complementing everything through a reading. Okay, prepare a very good notes, read NCERT. If you find any new facts in NCERT or something that might have been missed in the lecture, you just take a note of that in your notes as well. Okay, so this will help you in building up a very good notebook that will help you in revision of the topic. Okay, so let us start the main concept that which we wanted to cover today. Now this is called as colligative properties. Okay, now what are colligative properties? As you can see, this is written over here, the properties which depend upon the number of particles rather than the nature of the particle is called as colligative properties. Okay, so all those properties which depends upon the number of particles and not on the nature of particles is called as colligative property. Okay, common example which I can take over here is, the first I can say is molality. Okay, is molality a colligative property? Okay, now let me make you understand this through an example. If suppose, what is basically molality? It is the number of moles of solute upon mass of solvent in kg. Okay, so if we have taken more number of solute particles, okay, so the moles of solute will increase, hence the molality would also change. So this is one property which is directly depending on the number of particle, okay, rather than the nature of particle. If we are increasing the number of particles, the property is increasing, then we are saying that it is a colligative property. Okay, second we can say is molarity or the concentration term. Okay, this is also number of moles of solute upon volume of solution in liters. So if you if to a say like we are having say 100 ml of solution, you are adding say 658.5 grams of NaCl. So I will be preparing a 1 molar solution. Now if you add more number of NaCl, volume doesn't change much upon dissolution of solid in a liquid. So the volume would almost remain the same, only the number of moles of solute will increase. So we'll say that molarity is a colligative property. Similarly, if you look at the mole fractions, okay. So mole fraction is also basically the ratio of number of moles of one component upon the total mole. So these are all colligative property. Now the colligative property which we wanted to discuss in this chapter is relative lowering in vapor pressure. Okay, relative lowering in vapor pressure. Okay, so what is exactly relative lowering in vapor pressure? Now let us take an example to understand this. Suppose we are having a solvent. So initially we are having only the solvent, so the vapor formed would be of that of pure solvent. Okay, now when you add non-volatile solute to it, so we know that the vapor pressure of the solution would decrease. Now if you add more number of solute particles, so the vapor pressure would decrease to a much larger extent. So we say that relative lowering of vapor pressure is a colligative property. Vapor pressure itself is not a colligative property, because lowering of vapor pressure is depending upon the number of particles. So relative lowering in vapor pressure is a colligative property. Okay, vapor pressure is not a colligative property. Lowering is a colligative property because relative lowering depends upon the number of non-volatile solute added. Okay, so this is also abbreviated as RLVP. Okay, the next colligative property is elevation in boiling point. We are going to discuss this in today's lecture as well. So this is called as elevation in boiling point. The next is depression in freezing point, and the last is FP means freezing point, and the last is osmotic pressure. So we are going to discuss all these property. Okay, so just write it down, have a note of this. So the properties which depends only on the number of particles rather than the nature of the particles are called as colligative property. Here are some examples of the properties which are termed as colligative property. Just have a note of this. Excuse me. Okay, so let us start with the first colligative property, that is called as relative lowering in vapor pressure. Okay, so now we know that suppose we are having a solvent. So we know that the initial vapor that would be formed would be rich in the pure solvent A. So let us assume that these are the excuse me. So these are the vapors of the solvent A. Now suppose to this we add say a non-volatile solute. So we are adding some non-volatile solute. Okay. So let the vapor pressure of pure solvent be P naught A. Okay, initially only solvent was there, so the pressure developed would be that corresponding to P naught A. Now we have added some non-volatile solute. Now on adding non-volatile solute, what would happen? The non-volatile solute would dissolve in the solvent and would get distributed evenly in the solution. So there would be some solute particle that has come at the surface. Okay, now we know that the surface molecule can escape and go out as vapor, because now the surface is occupied by both volatile solvent as well as non-volatile solute. So the number of particles of the solvent at the surface would decrease because its position would be taken up by the non-volatile solute now. Okay, when you are adding a non-volatile solute to a solvent, so basically solvent get dispersed in the solution. solute get dispersed in the solution, it occupies the surface as well as the bulk evenly. Now at the surface, if you consider, now the surface was initially occupied only by the solvent molecules. Now when you have added solute particles into it, so solute particles will also occupy the surface, okay. So the number of solvent particles at the surface would decrease. Number of solvent particles at the surface would decrease, okay. So because the number of solvent particle at the surface has decreased, so the number of vapor formed of that particular solvent would be less. So we'll say that on addition of a non-volatile solute to a volatile solvent, the vapor pressure would decrease, okay. So let the vapor pressure of developed over solution, okay, the pressure developed over the solution is P, okay, or sometimes it also written as PS, okay. So this can be written as P naught corresponds to the vapor pressure of the pure component and PS correspond to the vapor pressure of the solution. Now when we have added the non-volatile solute, okay, we are assuming that the solution is a dilute one and it is obeying the Raoult's law. So we'll say that PS is proportional to the mole fraction of solvent, okay. The pressure developed over the solution would always be proportional to the mole fraction of that component in the liquid phase, okay. More is the component of that particular compound in the liquid state, more would be the vapor pressure. So this is what Raoult's law says that, okay, the vapor pressure developed over the solution is always proportional to the mole fraction of the solvent. So when you remove the proportional sign, you will get this as P naught X solvent, okay. Now we can easily make out from this expression, if X solvent is 1, it means that we are having only pure solvent, okay. So then the pressure would be equal to the P naught, that is pressure of pure solvent, okay. When you are taking X solvent less than 1, okay, so the pressure over the solution will start decreasing. It's a very simple mathematical expression. So if we want to write this, we can also write this as PS upon P naught. This will be equal to mole fraction of solvent. So we can also write mole fraction of solvent as 1 minus mole fraction of solute, because we know that mole fraction of solvent plus solute is 1. So the mole fraction of solute in this case would become 1 minus PS upon P naught, okay. So mole fraction of solute would be P naught minus PS upon P naught, okay. So if we look at this expression, so the pressure initially of the solvent was P naught, okay, or P naught A. When we have added non-volatile solute, now because the surface is occupied by some of the non-volatile solute as well, so the number of particles of solvent which we are escaping as the vapor on the surface would decrease, because the number of particles at the surface which are escaping out as vapor is decreasing, so the vapor pressure would decrease. So PS is the vapor pressure when the non-volatile solute has been added. So P naught minus PS is basically the lowering in the vapor pressure, okay. This is the quantity by which the vapor pressure has been lowered. When you divide it by P naught, so it becomes a ratio, so it is known as relative lowering in vapor pressure, and that is always equal to mole fraction of solute, okay. So if you add more number of solutes, okay, so the mole fraction of the solute would be more, so the relative lowering in vapor pressure would be more, okay. So this is again a colligative property because it is depending upon the mole fraction or number of particles, okay. Hope this is clear to everyone. You can just write it. We can also simplify this expression, because every time when we want to calculate, what we have to do, we have to write this as number of moles of solute upon number of moles of solute plus number of moles of solvent equals to P naught minus PS upon P naught, okay. So every time we have to calculate the number of moles of solute as well as solvent, then we want to add it and then we have to divide it to get the mole fraction. So if we want to just have the ratio of the moles, so what I will do over here, which just take the reciprocal of this expression. So when you take reciprocal, this becomes number of moles of solute plus number of moles of solvent divided by number of moles of solvent, okay. So this is equal to P naught upon P naught minus PS. So what I am doing exactly here, I am just taking the reciprocal. So I am just taking the reciprocal of the entire expression. Okay, now you can clearly see, I can write this as number of moles of solute divided by number of moles of solvent plus 1 equals to P naught upon P naught minus Ps. So if you have placed 1 over there, so I will get this as number of moles of solute upon number of moles of solvent equals to P naught by P naught minus Ps minus 1. So if you take this above, so we'll get the final expression as Ps upon P naught minus Ps. Okay, so we can also use this expression while solving the question. This is little, like, according to me, many of the students use this formula, many use this. Okay, this is relatively easy because you don't have to take the total number of moles. So just divide the moles, okay, the ratio of the moles of the solute and solvent, okay, and that is equal to Ps upon P naught minus Ps. But this expression is X solute is P naught minus Ps upon P naught. Okay, so this is basically relative lowering in vapor pressure. Also, it is abbreviated as RLVP. Okay, you can clearly see that the lowering of the relative lowering of the vapor pressure is equal to the mole fraction of solute. Okay, so it is depending upon the number of particles rather than the nature of particle, hence it is a colligative property. This expression is not called as relative lowering in vapor pressure. This is a relative lowering in vapor pressure. Okay, so just I have expressed this equation, this expression like this. So this is not RLVP, this is the expression for RLVP. This is just you can use for solving. Okay, for solving questions you can use this formula also. Okay, but RLVP is that. Okay, so just write it down quickly. Hope everyone has written it now. Okay, so let's look at one of the questions. So just solve it, read the question, just solve it. The question is saying the vapor pressure of a solution containing 13 gram of a solute in 100 gram of water at 28 degrees Celsius is 23.371 mmHg. Calculate the molecular weight of the solute. The vapor pressure of water at 28 degrees Celsius is 28.065. So obviously this is the vapor pressure of pure water. Okay, so this is basically P naught. Now when we have added the non-volatile solute, the vapor pressure we know will decrease. So this is the vapor pressure of the solution. Okay, now we have to calculate the molecular weight of the solute. So this is basically a question of lowering in vapor pressure or relative lowering in vapor pressure. Okay, so just use the formula, plug it and try to solve it. Okay, so we know that the formula of relative lowering vapor pressure is P naught minus Ps upon P naught is equals to mole fraction of solute. So let the molecular mass or the molar mass of solute be M. Okay, so we know that the number of moles of this solute is 13 upon M. Okay, the moles of solvent, which is water in this case, would be mass of water is 100 gram divided by 18. Okay, 18 is the molar mass of water. So we can write this as P naught was 28 minus 28.065 minus 27.371 divided by 27.371 equals to mole fraction of solute is moles of solute divided by total moles in the solution, which would be 13 by M plus 100 by 18. Okay, so you can solve this equation and you can get the value of M. Okay, so this is the direct application of the formula which we have derived. Okay, so this was the formula. Okay, you can also use this formula, which is number of moles of solute upon number of moles of solvent equals to Ps, that is pressure developed over the solution, divided by P naught minus Ps. So we know the number of moles of solute is 13 by M. number of moles of solvent is 100 by 18. This is equal to, the pressure developed over the solution was 27.371 divided by the initial pressure was 28.065 minus 27.371. Okay, so you can directly use this. Okay, so you can directly use this and you can solve the question. Okay, hope this is clear to everyone. This is a very basic question, direct formula, and believe me, JEE Mains will ask questions like this only. The questions in JEE Mains never goes beyond this. Okay, so a Van't Hoff factor concept which has to be done till now, so that can be incorporated, otherwise the questions are basically like this only. So you just have to use the formula, but you have to make sure that you are doing the calculations accurately. So that's why I am leaving this. I hope that after the class you are like doing the number crunching, you are doing the solving and you are getting the answer without using the calculator. Make sure that you are doing it every time whenever it is given to you, so that your calculation skills will increase. Okay. So let us solve this question now. It says that we have to calculate the relative lowering of air pressure of 1 molar aqueous solution of glucose, where pressure of water is given to us as 30 mm of Hg. Okay. So if you remember, we started the chapter with concentration terms. Like for all those who have joined newly or who have missed out those classes, and like all those who have also attended that. So basically the purpose of that class was to make us adjust with the different concentration terms and how different concentration terms can be interconverted. Okay, or the strength of the solutions can be interconverted. So this is one such question where we have to do the interconversion, and IIT asks these questions because it has two concepts, one that of solution and other that of mole concept. So we have been given the mole fraction of the molality of the solution as 1. Okay, so we have been given the molality of the solution as 1. Okay, for calculating the relative lowering in vapor pressure, we know that we need to have the mole fraction of solute, because the relative lowering in vapor pressure is equal to the mole fraction of solute. So we need to find the mole fraction of solute using this molality data. Now I have already done this conversion in the first lecture. If you have missed that, you can go and check it. So this is basically molality is equals to mole fraction of solute divided by 1 minus mole fraction of solute into 1000 divided by molar mass of the solvent. Okay, so this was the formula which we derived. So we know that molality over here is 1. Okay, so this is X solute divided by 1 minus X solute into 1000. The molar mass of the solvent is 18 because it is water. Okay, so you can take this entire term over here. So this would become 18 minus 18 X solute equals to 1000 into X solute. Okay, so I can write this as 1018 into mole fraction of solute is equal to 18. Okay, so clearly I can say that the mole fraction of solute is 18 upon 1018. Okay, so again you need to do a lot of calculation over here. Just do the calculation so that you become strong in calculating the different type of equations. Okay, so we know that the relative lowering in vapor pressure is P naught minus Ps upon P naught. So this is equal to mole fraction of solute. So answer would be this, 18 upon 1018. Now suppose if in this question it would have asked find the vapor pressure developed over the solution. So we know the relative lowering vapor pressure. So we know that P naught is as given as 30. We need to find the value of Ps. This is given as 30. So this is equal to 18 upon 1018. So I can also write this as 1 minus Ps upon 30. This is equal to 18 upon 1018. So I can take it over here. So this would be 18 upon 1018 equals to Ps upon 30. So this would be 1000 upon 1018 equals to Ps upon 30. So Ps, the pressure developed over the solution, would be 1000 upon 1018 into 30. Okay, you can clearly see that this value would be less than 1 because 1000 will be less than 30 because 1000 upon 1018 is less than 1. Okay, so this is how you can solve if in the question it was asked find the wave pressure developed over the solution when 1 molar aqueous solution of glucose is taken. The wave pressure of pure water was given to us, so we need to find the value of PS over here. Okay, so you can have a look. Hope this is clear to everyone now. Again, a very simple and a formula based approach question. Okay, so if you look at this chapter, the formulas you have to remember, okay, the basic theory behind those formula, the basic concept involved behind those formula, then you are done for this chapter. Okay, the difficult part in this chapter we have already discussed, that was the distillation, okay, of an ideal solution, the bubble point, the dew point, calculation of mole fraction at different, okay, point of time. Okay, I hope you have attended that lecture and you are clear with that, because questions in JEE will come from that segment as well. Okay, so let us just move ahead. So now the practical way of measuring the relative lowering of wave pressure is done through Ostwald-Walker process. Okay, now if we want to check the relative lowering in wave pressure, we need to do it through a process which is known as Ostwald-Walker process. Now what exactly happens in this process, how we exactly get the relative lowering in wave pressure through this method will be explained in just another 3 minutes. So just look at this. So what we are doing, we have taken a beaker containing the solution. Okay, now there are some tube attached to it. Okay, and finally the tube ends in the U-shaped closed tube which has weight or calcium chloride in it. Okay, so what happens over here is we are having a solution. Okay, so we know that the solution will develop a vapor pressure. Okay, so what we do is we pass air from over here. Okay, now this is the solution. Okay, you can clearly see that this is the solution, and then the later part there is a solvent. So initially the dry air passes into the solution. Okay, so this passes in the solution, you can see the passage, air enters from here. Okay, it will go inside, then it can come from here, it will go over here. Okay, the entire system is closed. Hope this is understood, obviously, because if you pass the air, you can also, like this can go out from here, but obviously the entire system is closed. So we are pushing the dry air, so the dry air goes inside the solution, it will like take this pathway. Okay, so it will again enter over here, it will come inside the solution, it will again go outside. Now in the second half of the segment, okay, we have taken there is a one solution system, there is one solvent system. So after passing through this, it goes into the solvent system. Okay, now from the solvent system the air will come out and it will go into the calcium chloride, again air will come out, it will go inside the calcium chloride tube, it will go inside and we'll get the dry air over here. Okay, so now let me explain what exactly is the role of dry air and how exactly is this setup working. So we have taken dry air over here, okay, free of moisture. Now when this is very obvious to everyone, like when there is a moisture in the air and when you blow a dry air over it, so the dry air which you blow over the moisture will be absorbed in the dry air. So basically the dry air would become moist. Okay, so when you take a solution, okay, we know that in a solution there would be some vapor pressure. Okay, so when we take a solution there is some vapor pressure. If you pass dry air over the solution, what would happen? The dry air would pick up the vapor that is formed in the container. Okay, because the air is dry, we know that the vapor of this solution would be formed. Okay, because water would be present as vapor over the solution. So dry air will pass through it and it will pick up the moisture. Okay, so basically dry air goes inside, when it comes out, so it will pick up the moisture from the solution, or it will pick up the vapor from the solution. Okay, so this goes inside, comes out, picks up the vapor of the solution, goes inside, picks up the vapor from the solution. Okay, hope this is clear to everyone. We are passing dry air through a solution. When we are passing dry air through a solution, so we know that in solution some vapor would be formed, vapor of the obviously solvent would be formed. In this case the solvent let us assume it is water. So we know that in a solution the vapor of water would be there, okay, which would be exerting some pressure on the surface of the solution. Now when you pass dry air through this, so dry air will basically pick up the vapor that has been formed over there. So the air which you pass through it will become eventually moist. So it will carry some amount of the vapor that is present in the solution, okay. So how this is measured now? Now what happens is we initially take the mass of the solution, okay, we initially take this mass of this solution. So the solution will have some mass, along with it some vapor. Now when you pass the dry air through it, okay, some of the vapor of the solution would be taken up by the dry air. So the mass of the solution container would reduce because its vapor has been taken away by the dry air, okay. So this loss in mass of the solution would be proportional to the amount of vapor that has been taken away by the dry air, okay. Hope this is clear. So we'll say that loss in weight of the solution would be proportional to the, okay, the amount of moisture that has been, the amount of vapor that has been taken by the dry air. The amount of vapor that has been taken by the dry air would be dependent upon the vapor pressure over the solution, okay. So it will say that loss in weight of solution is proportional to the vapor pressure over the solution, okay. Hope this is clear to you. So when you are passing the dry air, the vapor which is present above the solution will be taken up by the air, okay, by the dry air, and the dry air would become moist, and eventually the weight of the solution would decrease. So the loss in the weight of solution would be proportional to the amount of water or amount of vapor which the dry air is carrying. Now the amount of vapor in the solution, okay, would be proportional to its vapor pressure, okay. Now when this dry air comes out and when it passes into the solvent chamber, so we are having two chambers, first is the solution chamber and the second is the solvent chamber. So what will happen, again it will go in the solvent, it will take out the vapor of the pure solvent, okay. So the moist air comes over here, and when it enters into the solvent system, okay, so it will take up the vapors of the solvent now, okay. So the mass of the solvent system would also decrease. So initially suppose the mass of this was say m1, okay, when the air has passed through it, so the mass of this would decrease because some of the vapor of this solvent would be taken up by the air which you are passing. So we'll say that loss in weight of solvent would be proportional to, okay, because solvent is there, so there would be only pure vapor of the solvent, okay, or we can say that pure vapor of like water. So we'll say that this will be because initially it was also carrying the some moisture, because when this air was coming through the solvent system, so it was already carrying some vapor that was corresponding to PS. Now it will pick up some more amount of vapor from the solvent side, okay, and that would be proportional to the P0 minus PS, okay. So this would be the amount of the vapor that it would be picking up from the solvent side. Now when all of them passes through the calcium chloride tube, now basically the role of the calcium chloride is to absorb moisture. We know that calcium chloride absorbs moisture, it is a very good drying agent. So when you pass this moist air through weighted calcium chloride tube, so all the moisture that was taken up from the solution as well as solvent side would be absorbed in this, okay. So when the dry air which has become moist after passing through the solution and the solvent chamber, it would have become moist. Now when it passes through the calcium chloride tube, so all the moistures that it absorbed would be, okay, absorbed over here. So the air which would be finally coming out is dry. So what will happen? The weight of this overall calcium chloride tubes will increase. So suppose initially the weight of the calcium chloride before passing the air was m1. Now because when you are passing the moist air, it will absorb the moist air, okay, it will absorb the moisture. So the weight of this calcium chloride tube will increase. So the gain in weight of calcium chloride tubes would be proportional to the total amount of vapor that they are absorbing. So total vapor that they would be absorbing is PS, which is coming from the solvent side, plus P naught minus pH, which is coming from the solute side. So this will be proportional to P naught. Okay, so we'll say that relative lowering in vapor pressure we know is P naught minus PS upon P naught. Okay, so we'll say that this is loss in weight in the solvent chamber. Okay, loss in weight in the solvent chamber divided by the gain in weight of calcium chloride chambers. Okay, hope this is clear to everyone. Okay, so hope this is clear to everyone. So you can just write it. So this is the experimental way of determining the relative lowering in vapor pressure. ठीक है, तो यहाँ पर अगर आप देखोगे तो कर क्या रहे हैं हम बेसिकली ड्राई एयर पास कर रहे हैं और हमारे पास एक सॉल्वेंट सिस्टम, एक सोल्यूशन सिस्टम है. पहले ये ड्राई एयर सोल्यूशन सिस्टम से पास हो रहा है, पास होने के बाद फिर ये सॉल्वेंट सिस्टम में जा रहा है, सॉल्वेंट सिस्टम से निकल कर ये कैल्शियम क्लोराइड ट्यूब की तरफ जा रहा है. तो जब इनिशियली ड्राई एयर अंदर जाएगा सोल्यूशन में, तो सोल्यूशन के ऊपर सोल्यूशन का वेपर बना होगा. ओके, कितना वेपर बना होगा वो उसके वेपर प्रेशर पे डिपेंड कर रहा है. तो जब ये ड्राई एयर सोल्यूशन के अंदर जाएगा तो ये बेसिकली ड्राई एयर क्या करेगा कि यहाँ पर जो भी वेपर प्रेजेंट थे सोल्यूशन के ऊपर उनको वो साथ लेके चला जाएगा, बिकॉज एयर ड्राई है. ओके, मॉइस्चर लेके वो चला जाएगा. तो बेसिकली जब यहाँ से ये पास किया तो ये जो ड्राई एयर था यहाँ आते आते सॉल्वेंट में जाने से पहले वो मॉइस्ट में कन्वर्ट हो चुका है. तो ये जो साइड था सोल्यूशन साइड, इसका कुछ वेट होगा इनिशियली. एक बार जब हमने एयर पास कर दिया उसके बाद इसको निकाल के वेट करेंगे तो उसका वेट कम आएगा. कम क्यों आएगा? क्योंकि यहाँ पर पास करने के बाद ओके जो वेपर था, कुछ वेपर वाटर के साथ एयर के साथ चला गया तो वेपर का मास कम हो जाएगा. सो जो लॉस हुआ होगा वेट का सोल्यूशन साइड में वो हमेशा प्रोपोर्शनल होगा द वेपर प्रेशर डेवलप्ड ओवर द सोल्यूशन. ओके, नाउ उसके बाद जब ये ड्राई एयर सॉल्वेंट साइड में जा रहा है, ओके तो सॉल्वेंट के ऊपर सिर्फ प्योर सॉल्वेंट का वेपर बना होगा, बट ऑलरेडी जो एयर था वो मॉइस्ट हो चुका था, उसके अंदर ऑलरेडी मॉइस्चर था क्योंकि वो सोल्यूशन से पास होकर आ रहा था, तो उसमें ऑलरेडी पीएस का ठीक है अमाउंट प्रेजेंट है पहले से. तो अब जो वो वाटर पिक करेगा दैट वुड बी पी नॉट माइनस पीएस. ओके, सो द लॉस इन वेट ऑफ दिस साइड वुड बी पी नॉट माइनस पीएस. उसके बाद जब हमने कैल्शियम क्लोराइड में इसको पास किया तो सारा जो मॉइस्चर यहां से उसने एब्जॉर्ब किया होगा वो सारा मॉइस्चर कैल्शियम क्लोराइड ट्यूब में चला जाएगा और फाइनली एयर ड्राई होकर बाहर निकल जाएगा. तो ये जो कैल्शियम क्लोराइड का ट्यूब जितना मास गेन किया होगा दैट विल बी प्रोपोर्शनल टू द टोटल okay vapors that were present over here. Okay, so it would be the sum of these two. So we'll say that the gain in weight of calcium chloride tube is proportional to P naught. Okay, so hope this is clear to everyone. You can just write it. There are direct questions on this. Okay, so questions will be written and you can directly plug the value and you will get the relative lowering in vapor pressure. From relative lowering in vapor pressure we know that it is equal to mole fraction of solute. You will get the value of mole fraction of solute. We can also calculate the molality of the solution. We know that molality of the solution is mole fraction of solute upon 1 minus mole fraction of solute into 1000 divided by molar mass of the solvent. Okay, so just write it down quickly. Okay, you can draw a rough sketch of this process also. This is known as Ostwald-Walker process. Okay, there are some questions on this in the today's daily practice problem sheet. So you can go through those questions. You will see how these formulas are applicable over there. Okay, so for all those who are not solving the daily practice problem sheet and just viewing the lecture and just solving their own content, I would request you to just go through the daily practice problem sheet. Is there on the Yup Master application. So you can just solve those questions. That would actually help you or assist you in memorizing all the important facts that we are covering in lecture, because that has question related to only this lecture. So we'll get a lot of insight of different type of questions that can be formed. Okay, so hope you are writing this. Take 1 minute and just write it down quickly. Okay, so just read this question, just solve this question. Okay, so this question is basically based on the Austral-Walker process. So this says that a current of dry air was bubbled through a bulb containing 26.6 gram of organic substances, 200 gram of water, then through a bulb at the same temperature containing pure water, and finally through a tube containing fused calcium chloride. Okay, the loss in weight of the water bulb. Okay, so we know that loss in weight in the solvent chamber, in this case solvent is water, is always proportional to P naught minus Ps. Okay, so we know that P naught minus Ps, okay, P naught minus Ps is proportional to, so this is proportional to 0.087 grams, okay, and the gain in weight of calcium chloride tube. So we know that gain in weight in calcium chloride tube is proportional to P naught. Okay, so we know that P naught is proportional to, it is given as 2.036. Okay, we need to find the molecular weight of the organic substance in the solution. So we know that relative lowering of vapor pressure is also equal to mole fraction of solute, which is P naught minus Ps upon P naught. Okay, so we know the value of P naught minus Ps as 0.087, and we know the value of P naught is proportional to 2.036. Now the mole fraction of solute would be moles of solvent, moles of solute upon total moles. So moles of solute in this case would be, we know the mass of solute is given to us as 26.66. So let the molar mass of the unknown compound be M. So the moles of solute would be 26.6 divided by M. Now the total moles we know is moles of solute plus moles of solvent. Now the mass of water is 200, so this would be the mass of solvent. Okay, so from this you can calculate the value of M. Okay, so this would be 26.66 divided by M equals to, we can write this as 87 upon 2036 divided by into 26.66 upon M plus 200 upon 18. Okay, so from here we can find out the molar mass of the unknown compound. Okay, so again it involves a calculation. So I am leaving the calculation expecting that you are doing the calculation on your part after the class. Okay, because IIT will have integer type question up to 2 decimal places where you have to carry out such kind of calculations. Okay, so just have a look at the question. You can take a snapshot or you can write it quickly. Okay, hope the steps are clear to you and the question is clear to you, because if you are clear with the Austral-Walker process, then this question is a cakewalk, nothing difficult, just pure application of the formula, just plugging the values in the formula and you will get the answer. Okay. Now the second important colligative property is elevation in boiling point. Okay. Now to understand elevation in boiling point, let me define 2 or 3 important parameters through which we will be able to explain this in a much effective manner. Okay. Now the first thing that should come in your mind now is, what is basically boiling point? Okay, how do you define boiling point? Now till now, like in our junior classes, we were saying that when we are heating any liquid, okay, the temperature at which the liquid start forming its vapor is called as the boiling point. Okay, at say 1 atm. Okay, so this was the basic definition that we were giving in the junior classes, but that is not scientifically correct. Now the boiling point of a solvent is defined as the temperature at which the vapor pressure of the solvent becomes equal to the atmospheric pressure, okay, or the external pressure. So we say that the boiling point of, you can write it down as well. So the boiling point of a solvent is the temperature at which the vapor pressure of the liquid becomes equal to that of the external pressure. Okay, so there is a one boiling point, and we call another very important term, that is normal boiling point. Okay, so normal boiling point, it is the temperature. Okay, so it is the temperature at which the vapor pressure, it is the temperature at which the vapor pressure of the solvent becomes equal to the external pressure. In this case, we will say that external pressure is atmospheric pressure, okay, which is 1 atm. Okay, so the temperature at which the vapor pressure of the solvent becomes equal to the external atmospheric pressure, which is 1 atm, then that temperature is called as normal boiling point. Normal boiling point of water at 1 atm is 100 degrees Celsius. Now just remember, you have to mention the pressure for defining the boiling point, because if we change the pressure, surrounding pressure, then the boiling point would also change. Okay, so to understand, let us consider an example. Suppose we are having a container in which we are having some liquid. Now we know that liquid has formed some vapor. Okay, now to escape them completely out of the solution into the surrounding, okay, so what is happening? The vapors are bubbling out, they are coming from the surface. If the external pressure is more, so these bubbles or these vapor cannot escape out of the solution. So what we need more and more of vapor, and these vapors should be energetic enough to push the surrounding and come out as a vapor. So what we keep on doing, we keep on increasing the temperature. On increasing the temperature, we know that the kinetic energy of the molecule increases, the surface of the liquid becomes agitated, the vapors that are escaping out or the molecules that are escaping out will exert more vapor pressure. So if that bubbles which are coming out or the vapors which are coming out from the solution has pressure at least equal to the atmospheric pressure, they will come outside the solution and they will escape as the vapor. So that temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure, that is 1 atm, is known as normal boiling point. Okay, now let us again consider the same example. Now to this solvent we are adding some non-volatile solute. Okay, now when we have added non-volatile solute, we know that upon addition of non-volatile solute, the solute will get distributed in the entire solution now. Okay, the solute molecules will also occupy the surface of the liquid solution. Okay, so initially what was there at the surface? Only there was solvent molecules. Now when you have added the solute particles, non-volatile solute particles, the surface will be occupied both by solvent as well as solute particles. So the number of solvent particles which are escaping out from the solution as vapors into the surrounding would decrease, because the surface is now also occupied by the non-volatile solute. So the number of particles of solvent molecule which is escaping out of the solution would decrease. Okay, so as a result of which the vapor pressure of the solution decreases. Okay, so let me explain you once if you are not able to understand. अगर हमारे पास एक solvent है तो इनिशियली हमारे पास क्या होगा? सिर्फ solvent का वेपर होगा, सही है. ओके, जब हमने उस पर सल्यूट डाल दिया तो अब सल्यूट क्या करेगा? सल्यूट आके उसके सरफेस पे बैठ जाएगा, सोल्यूशन के सरफेस पे सल्यूट भी आ जाएगा. पहले जब सिर्फ सॉल्वेंट था तो सॉल्वेंट के सरफेस पे सिर्फ सॉल्वेंट के पार्टिकल्स होंगे, तो इनिशियली सिर्फ सॉल्वेंट के पार्टिकल्स एस्केप कर रहे थे, क्योंकि जो एस्केपिंग टेंडेंसी होगा वो सरफेस के ऊपर ही होगा, सरफेस से मॉलिक्यूल बाहर निकल के जाएंगे. अगर हम कैसे भी करके सरफेस को ब्लॉक कर देंगे या सरफेस पे नंबर ऑफ पार्टिकल्स जो एस्केप करके बाहर जा रहे हैं उसको कम कर देंगे, तो जो वेपर बनेगा वो कम बनेगा. अगर वेपर कम बन रहा है इसका मतलब वेपर प्रेशर कम आएगा. तो जब आपने इसमें नॉन वोलेटाइल सॉल्यूट डिसॉल्व कर दिया है तो सरफेस के ऊपर अब नॉन वोलेटाइल सॉल्यूट भी आ जाएगा. अब ये नॉन वोलेटाइल सॉल्यूट सरफेस से बाहर जा नहीं पाएगा. ओके, और सरफेस के ऊपर नंबर ऑफ सॉल्वेंट पार्टिकल्स कम हो जाएगा, तो नंबर ऑफ पार्टिकल जो एस्केप कर रहा है वो कम हो गया, जिसके कारण हम बोलते हैं वेपर प्रेशर भी कम हो गया. ओके, सो व्हेन द वेपर प्रेशर हैज रिड्यूस्ड नाउ, सो टू मेक इट बॉयल, टू मेक द सॉल्यूशन एस्केप एज वेपर इनटू द सराउंडिंग, वी नीड टू हीट इट मोर. ओके, क्योंकि प्रेशर कम हो गया है. बॉइलिंग पॉइंट तब अचीव होता है जब वेपर प्रेशर एटमॉस्फेरिक प्रेशर की इक्वल हो जाता है. बट नाउ व्हेन वी आर हीटिंग वी हैव टू हीट मोर because the vapor formed initially was less, so we have to heat more so that the vapor pressure becomes more and more, and finally it becomes equal to that of the atmospheric pressure so that it starts boiling and the vapors are forming and they are going outside into the surrounding. So you can see that when we have mixed a non-volatile solute in a particular solvent, so the boiling point of that solution increases. Okay, so this is called as elevation in boiling point. Boiling point elevate ho gaya, boiling point बढ़ गया. So this is called as elevation in boiling point. So when you add a non-volatile solute to a solvent, okay, so the boiling point of the solvent increases because its vapor pressure has decreased. So we need to heat the system more so that it changes into the vapor phase, so that more and more vapor are formed and it becomes equal to the vapor pressure of which becomes equal to that of the external atmospheric pressure. Okay, so when you add a non-volatile solute, we are saying that the boiling point of the solvent would increase. Okay, now on which factor it would depend? If we add more and more of non-volatile solute, so the vapor pressure of the solution will keep on decreasing because more and more number of solute are there. So the number of solute particle at the surface of the solution would increase, keep on increasing. So the number of particles escaping out from the solution into the vapor phase would also decrease because number of solvent particles on the surface is decreasing, as a result of which the vapor pressure would decrease. So we have to heat even more so that the vapor pressure becomes equal to the atmospheric pressure. So this elevation in boiling point is dependent upon the number of solute particle added. So that's why it is also a colligative property. So elevation in boiling point is also a colligative property because it is depending upon the number of particles of non-volatile solute added in this case. Okay. Hope this is clear to everyone. So you can have a look at this. We'll sketch the phase diagram of water in the next lecture. I will explain you what is phase diagram. So here what we have done, we have plotted vapor pressure versus temperature. So this is basically there are two lines given over here. Okay, so this is basically your solvent line. Okay, so this is your basically solvent line. Okay, now when we have added non-volatile solute to it, so we know that its vapor pressure would decrease. So this line would represent the vapor pressure variation of the solution. Okay, so you can see that at any point, okay, so at any point the vapor pressure of the at any temperature, if you take any temperature, you can see that the vapor pressure of the solvent would be more than that of solution. So we know that, okay, so at any particular temperature the vapor pressure of the solvent would be more than that of solution. Okay, so we know that we have added a non-volatile solute and its boiling point has also increased. So we know that the boiling of the normal boiling point is achieved when the vapor pressure becomes equal to that of atmospheric pressure, which is 1 atm. So let this be 1 atm. So if you just draw a line over here, so at this point, okay, the temperature corresponding to 1 atm would correspond to the boiling point of the pure liquid, okay, because this is the solvent line. So when the vapor pressure becomes equal to 1 atm, the temperature corresponding to it is known as the boiling point. Okay, now if you look for the solution is this one. Okay, so if you look at the solution, so when the pressure is 1 atm, you can see that the boiling point of the solution is Tb. Okay, you can clearly see that the value of Tb is greater than T naught B. So this difference in temperature is known as elevation in boiling point because boiling point has increased. So this is known as elevation in boiling point, which is Tb minus T naught B. Okay, hope this is clear to everyone. Okay, so we can derive the formula as well, but I am not going into the derivation. I will directly say that delta Tb is proportional to the number of particles of the solute added. So number of particles of the solute added. So I can write that Tb is proportional to the molality. Okay, so this can be derived by having a similar triangle concept, okay, joining them as a triangle and then deriving the formula. Derivation of formula is not important at this stage. If you know the formula, you can easily handle all the questions. Okay, so we know that the elevation in boiling point will be proportional to the amount of solute added. Okay, so that is denoted by molality because we know that molality is also a colligative property. So delta Tb is proportional to the molality of the solution. Now when you remove this proportional sign, okay, we get a constant known as Kb. Okay, so this is basically delta Tb is equals to Kb into m. What is delta Tb? Delta Tb is boiling point. Tb is your boiling point of solution minus boiling point of the pure solvent. Okay, so this is boiling point of solution. Tb naught is the boiling point of the solvent. So when you add a non-volatile solute to a volatile solvent, the boiling point of the solvent would increase. The elevation in boiling point or the increase in boiling point would be the boiling point of the solution minus the boiling point of the solvent. Okay, so m over here is molality. Okay, now if you look at Kb, now what does Kb signifies? Now we'll say that Kb here is called as ebullioscopic constant. Okay, so this is called as ebullioscopic constant, or also called as boiling point elevation constant. Okay, so molal boiling point elevation constant. So we can define it as, this can be defined as, it is the elevation in the boiling point for a 1 molar solution. So when the molality is 1, so we know the value of Kb would be equal to delta Tb. So we'll define it as, it is the elevation in boiling point for a 1 molar solution. Okay, for a 1 molar aqueous solution. Hope this is clear to everyone. Okay, so this is basically called as ebullioscopic constant, molar elevation constant, or boiling point elevation constant. You can call it, okay, anything between these three, molar elevation constant. Okay, so Kb for water in general is, okay, if you look for the unit of Kb, so the unit would be, because the difference in temperature is there, so that unit would be either Kelvin or degree Celsius, and we will have delta Tb upon m as the value of Kb. So delta Tb, I can write this as degree Celsius per molal. Now molal is basically number of moles upon mass of solvent in kg. So I can also write this as, okay, moles per mole kg. Okay, so hope this is clear to everyone. We can write it degree Celsius or degree Kelvin. Okay, now the unit of molality is number of moles upon mass of solvent in kg. So number of moles is basically moles, and solvent is taken in kg, so this is kg. So this is mole per kg. So unit of this would be degree Celsius per mole, okay, into kg. Okay, so just have a quick glance over this, and just you can write it down quickly. So we say that whenever to a pure solvent we are mixing any non-volatile solute, or we are mixing any solute, so the boiling point of that solution or the boiling point of that particular solute will increase. So on addition of a non-volatile solute to a solvent, the boiling point increases, and the elevation in boiling point is a colligative property. It is proportional to the molality of the solution. So I can write delta Tb equals to Kb into m, where this Kb is called as ebullioscopic constant, molar elevation constant, or boiling point elevation constant. Okay. So there are two methods through which it can be, elevation in boiling point can be determined experimentally. We don't have to go in the detail, just we'll remember the name. So experimentally, delta Tb or the elevation in boiling point can be determined by okay, there is one method called as Cottrell's method. Okay, so experimentally it can be determined by Cottrell's method. Okay, just write it down. So just write down the formula. Okay, I hope you have written this down. So there is a special thermometer which is known as Beckman thermometer. Okay, so that measures the temperature. So experimentally it can also be determined through Beckman's method. Okay, so we are not going into the detailed setup of these experiments. So you have to remember the name, that would be enough. Okay. So we have defined Kb, okay, as the elevation in boiling point for 1 molar aqueous solution. So if you look at the value of Kb, so Kb is basically given as R into Tb square, okay, into the molar mass of the solvent divided by 1000 into delta H vaporization. Okay, so let me just make you understand what are the various terms over here. Okay, so in this case delta H vaporization is enthalpy of vaporization of the liquid, enthalpy of vaporization of whatever solvent we are talking about, enthalpy of vaporization of solvent. Okay, M solvent is the molar mass of the solvent. Okay, R is your gas constant. Okay, Tb is the boiling point of pure solvent. Okay, so we are basically finding the value of Kb or the ebullioscopic constant for solvents. So we know that Kb is a constant, so this will have a constant value for a particular solvent. Okay, if you keep on changing, the solvent, the value of Kb will change. The value of Kb for water is 0.2 degrees Celsius kg per mole. Okay, so this will keep on changing if you change the solvent. If you change the solvent from say water to carbon disulfide, the value of Kb will change. As you can clearly see that the Kb value depend upon the boiling point of pure solvent. Okay, R is the gas constant, R Tb square into molar mass of the solvent divided by enthalpy of vaporization of the solvent. Okay, this can also be written as R Tb square upon 1000 into latent heat of vaporization. LV is your latent heat of vaporization. Latent of vaporization is basically delta H vaporization upon molar mass of solvent. Okay, so LV is here latent heat of vaporization. Okay, so this is how you find out the value of Kb. Okay, we come to know about the boiling point of the pure solvent. We know the molar mass, we know the value of gas constant, that is R. Okay, and we know the value of delta H vaporization of that particular solvent. So we'll be able to calculate the value of Kb for a particular solvent, and it is constant for a particular solvent, and it will change if you change the solvent. Kb for water is generally 0.52 per degree Celsius kg per mole. Okay, so just write this formula. We'll just quickly solve 1 or 2 questions on this before ending the session for today. You can solve the daily practice problem sheet. Read NCERT. I am always telling you to read a theoretical book just after your lectures, so that whatever you have studied in the lecture, you will be able to understand how scientifically things are done. Okay. So I hope you have written this now. So we have to remember the formula delta Tb is equals to Kb into M. Okay. So just look at this question. Now this question says that there is a solution which is containing 3.24 gram of a non-volatile non-electrolyte solute and 200 gram of water, boils at 100.13 degrees Celsius at 1 atm. What is the molecular weight of the solute? Kb for water is given as 0.513 degrees Celsius per mole. Okay. So in this case we can say that delta Tb is Kb into M. Okay. Now delta Tb is basically the boiling point of the solution minus boiling point of the pure solvent, which is water in this case. Okay, so we know that the boiling point of pure water at 1 atm is 100 degrees Celsius, which is not given, but not given, it is given that it is 1 atm. So you can easily understand that it is 100 degrees Celsius. So I will say that delta TB is equals to 0.13 degrees Celsius. Okay, so delta TB would be Kb into M. Okay, so we know the value of delta TB, which is 0.13. Kb we know is 0.513. Molality is basically number of moles of solute upon mass of solvent in kg. So number of moles of solute we can calculate upon mass of solvent in kg. So we know that the mass of solvent in water is 200 grams, so which is 0.2 kg. So we can get the number of moles of solute as 0.13 into 0.2 divided by 0.513. Okay, so we have got the number of moles of solute. From there we can get the molar mass of the solute. We know that the number of moles of solute would be mass of solute, which is 3.24 upon molar mass of the solute. Okay, capital M is representing molar mass and not molarity. Okay, so whenever I am writing capital M solute, it means molar mass of solute, capital M solvent, molar mass of the solvent. So this is 0.13 into 0.2 upon 0.513. So the molar mass of the solute in this case would be 3.24 into 0.513 divided by 0.2 into 0.13. Okay, so you can just plug the value, you can get the molar mass of the unknown solute. Okay, so this is a very straightforward question. Okay, so finally this would be the answer. Okay, just read the question. You can see this is a very simple question just based on the formula, and questions in this chapter is basically formed only on the formulas. Okay, so I hope you have written this now. So let us look at the last question. Okay, so this says that what will be the boiling point of bromine. Okay, bromine is a liquid when 174.15 milligram of octaatomic sulfur. Octaatomic sulfur means S8. Okay, now we know that sulfur has a molar mass of 32. So molar mass of S8 would be 32 into 8, that is 256 gram per mole. Okay, so this says that what will be the boiling point of bromine when 174.5 milligrams of octaatomic sulfur is added to 78 gram of bromine. So we can understand that bromine is the solvent over here. Okay, so solute is our octaatomic sulfur. So we can write the number of moles of sulfur would be, that is 0.1745 grams divided by molar mass of sulfur, which is 256. Okay, so we know the mass of bromine, which is solvent, which is 78 into 10 raised to minus 3 kg. Okay, so the molality of this solution would be number of moles of solute, which is 0.1745 divided by 256 upon 78 into 10 raised to minus 3. So from this data you can calculate the molality. Okay, now we know that delta TB is equals to Kb into M. Okay, the value of Kb is given to us as 5.2 Kelvin per mole per kg. Just look on the units as well. Now because it is expressed in terms of kg, so when you multiply with molality, molality is also expressed as per kg, so they get cancelled out. So if this would have been in gram, so you have to convert this also into kg. So these are the small things that you should take care of, because IIT frames question on this. So you need to check that the formulas which you are using are matching the dimensional analysis. Okay, so this would be into molality. So molality we know is 0.1745 upon 256 divided by 78 into 10 raised to minus 3. So this would be the elevation in boiling point. So elevation in boiling point is the boiling point of the solution minus boiling point of the pure solvent, which is bromine in this case. This would be 0.52 into 0.1745 divided by 25 into 78 into 10 raised to minus 3. So we can get the boiling point of pure solution as, okay, the boiling point of pure bromine was 332.15 plus 0.52 into 0.1745 divided by 25 into 78 into 10 raised to minus 3. Okay, so this would be the boiling point of this solution bromine when 174.5 milligram of octatomic sulfur is added to it. Okay, so this is again just formula based. So the calculations are little difficult to carry out, I can understand. Okay, so just you can use some approximation tools to carry out the calculation, but in JEE definitely calculations will not be of this type. It will be at least in a number that can be easily calculated. Okay, so this is one such question. You can just read the question and have a quick glance at the solution. Okay, so I hope you have taken the snapshot of this question. You can take a snapshot of this question after the lecture. You can attempt those questions again, okay, without looking at the solution. So that will ensure that you are understanding all the concept. Okay, so this is it for today.